to talk about yesterday's exam. So we have a shaft, the shaft that we see all the time, right? I have been using this shaft for a long while. Okay, so there is bearing on both sides, and there are some parts that has thicker diameters, and there are distributed loads from the belt. Okay, so from here to here is 90, and here is 60, and then 150. This is 60, and here is 90. Okay, and you have pulling force on top. Pulling force on top. So, and W1, W2 are 12 and 40, right? The other one is 48 and 20. Okay? And the diameter of the thinner part is here is 40, and the thicker part is 60, right? And the fillet is 3. Yielding strength is 300. Ultimate tensile strength is 650, and the endurance limit is 250. What else? So all the numbers are here. Okay, and the shaft is rotating. Okay. So how do you solve this? Yesterday, some students asked about how do you determine the fluctuating condition for this, because this is rotating. So if you pick up an element on the shaft, it will be experiencing tensile and compression when along the cycle. So that's how you can analyze the fluctuating level. Okay, so reaction forces. So if you say this is R1, this is R2, so we can do some math here. So the total is 52. Total is 68. So if you treat this one as a support point, then this is 52 times the width, 60, multiplying the radius up to here. So this is 120. So this gives you a counterclockwise moment. The other part plus 68 times the width, 60 times the distance up to here. So that would be that was 120 here. So that would be 150, 300, 330. Okay. And this one also counterclockwise. So R2 times the total length total length would be 120, 180, 300, 450. So 450 50 equals to 0. Okay? So this is how you can get R2. And if you put a support point right here, you do the same thing, but this time will be clockwise. So 60A times the width, 60, times the distance, the same 120. This problem is a little bit symmetric, left and right. Plus 52 times 60 times 330 plus R1 times 450. So this is how you can get the first problem, R1 and R2. Okay? And they should be some negative values. There will be some negative values. The second problem would be you should, let me quickly get the number. So 52 times 60 times 120 plus 68 times 60 times 230 divided by 450. So okay, and then here is 68, 52, okay,
25, it should be 52.
oh, did I make a mistake?
Yeah.
Sorry.
No, this, if you go here,
Yeah.
you put 25, I think.
Ah,
it should be
sorry.
52.
Thank you. Okay, thank you. Okay. So next you can draw the shear diagram. It's the shear along y direction. Okay. So over here you have negative R1, so 3376 going down, right? And then up to here, same. Then you have 52. The slope should be 52, and then going up. So it would be something like this. Let me see how much. 52 times 60. 52 times 60. That's 3120. So this is 3120 up to here. And then going right, and you will go up again. 68 times 20. So 4080. Here, 4080. And then go to the right, go down. So here should be, supposedly it's 3824. Okay, so that would be your shear diagram. Then, sorry. You can then work on the moment. So what I always do is to formulate the equations. So there are 5 different portions. First part is negative 3376. Next part will be 52x plus a coefficient right here. So I can say C1. And then the other part would be, I can quickly do the math. 3376 minus 3120. So that would be 256. Okay, the level right here is 256. And then the next part would be 68x plus C2. The last part will be 3824. Okay, so now I need to get values of C1 and C2. And so here is negative 256. I can plug in, here is 90, no, not, yes, 90, and here is 150, and here is 300, here is 360, and then 450. And I can now plug in numbers. Negative 256 equals to this part of linear equation 52 times the position 150 plus C1. So that gives you C1. So C1 equals to some negative value. Negative 256 minus 52 times 150. So A056. Then this part I'm going to use the 300. So negative 256 equals to this equation, 68 times 300 plus C2. So C2 equals to, this is 68 times 300. So 20656. Okay? So that gives you the equations in the shear diagram. So if you do the integral, you will get all the equations you need for the moment. So the moment part will be negative 3376x plus, you don't need a plus anymore because based on the boundary condition, here is 0. Okay, so that's it. The next part would be 26x squared plus C1, so minus, I forget about negative sign here. So minus A056x plus C3, okay? The other part, negative 256x plus C4, and then 68 divided by 2, 34x squared. C2 is right here, minus 20656x plus C5. Last one, 3824x plus C6. Okay, so you can now plug in numbers to get every part. So at the end, it will look like this, and it will look like a little bit like this, and then look like this, and something like this, and go up. Okay. So that's how the equation, how the moment diagram look like. So the worst bending condition will be somewhere close to here. So it's either at the intersection between part 3 or part 4, or somewhere at the bottom of the part 4. So we can try to solve for the minimum value of part 4. Okay, so if you take the derivative of the part 4, then you can get the slope. So after you take the derivative, you actually have 68, actually that's this one, 68x, and then minus 20656. You want this to be 0. So that gives you the extreme value. So from there you can tell where is the location of the extreme. 656 divided by 68. So 303, I will just round it. So 304. So somewhere here, like this corner is 300. So 4 millimeter on the right, that's where you have the extreme value. So right somewhere here. That's the worst bending position. The position with the largest bending moment. Okay, that's how you can get the maximum bending. So that's next to the position of 300 millimeter. Now, you now need to do the fatigue model. So, in order to apply fatigue model, you basically analyze right at this position. Okay. So you kind of need to care about the stress concentration effect close to this corner. Okay. Now, the stress equals to 32 m over pi d cubed, right? So right here you will be you need to plug in to this equation in order to find out what's the extreme value. I don't have it right now, but it's a value. It's some value. And then how about the shearing stress? It's a 16T over pi d cubed. So the moment can be determined by obtaining this greatest moment. So that value is basically this m right there. How about torque? Torque will be here 40 and 12, so the difference is 28. 48 and 20, so the difference is 28. So actually it's 28 times the radius, the top, right? The radius. So the radius of this part is 30. So the top is 28 times 30. So that's how you can get the torque value right there. And for the small d right there, you need to use the critical diameter. You need to use the small d, not the big one. That's how you can get worst stress condition. So this small d would be the small diameter right there. So that would be 40. Okay, so plug in all the numbers. And you can now, for example, take a look at one of the points, let's say on the top. And over there, because this is how the shaft is being bended like this. Right? If you exaggerate, this is like being pulled down, and this is being pulled up. Right? So you are starting somewhere here. And you are now focusing on a point on the very top of the shaft, it has been pulled left and right. So if you draw the stress diagram, this will be your stress. And then depends on how you twist the element. W2 is larger, so this is twisting this way, this is twisting this way. It's like this. So if you are focusing on element right here, so on its left hand side, it's like twisting up. So the shearing force on the left goes up, and here goes down. And this is how you make it symmetric, right? So that would be the a diagram for the stress. Then you can draw a Mohr circle. Here is stress, here is your shearing stress. This is your, if you are focusing on this point, and if you say counterclockwise is positive, this one is clockwise. So you would have a negative shear right here for this particular point. And if you go up, then it's positive shear, no normal stress. So it will be some point right here. So that's how you can draw a straight line and then form a circle. Okay? And over here, you can then compute for the principal stresses, S1 and S2. Okay, so this is the Mohr circle for this particular point on the top. But when it goes to the bottom, it's a different scenario. It's a completely reversed. Completely reversed. So when it goes to the bottom, when it's completely reversed, so the Mohr circle, when it goes to the very bottom, it's actually like this. It's like a mirror of this. So the S1, the position, the element that you pick up, when it's on the top, it's right here. But when it goes to the bottom, it's going to the very left. And this point is going to the right. So from here you can see S1 and S2 up. I ask you to compute for the fluctuation of the moment. They don't. So they are, in this case, it depends, so right here, they are zero. The amplitude is zero. So this is the end, and this is the torque from here and here. Okay, they don't fluctuate with time. So this will be zero. Okay, this will be zero. However, we are studying the fluctuation of von Mises stress. Von Mises stress fluctuates because the ship is rotating. So how do you study for the fluctuation of the von Mises stress? Von Mises stress is right here. S1 squared plus S2 squared minus S1 S2. Okay? Does it fluctuate? If you study for the S1, So as time goes, so this is S1, so it will be going up and down. So the mean of S1 mean equals to 0. S1 amplitude equals to whatever S1 you determine right there from Moore circle. Okay? Okay. And similarly, S2 mean equals to 0 because it's fluctuating and like a sine wave. But the S2 amplitude equals to the X2 you determine from the Moore circle. Okay? So, it's an interesting problem where the stress von Mises mean actually equals to 0. But the S von Mises amplitude will be determined by S1 amplitude squared plus S2 amplitude squared minus S1 amplitude, S2 amplitude. Okay, so that's actually how the fluctuating situation happening for von Mises stress. Okay, and then I asked you to solve it by Soderberg model. However, I need you to apply the stress concentration factor. So where do you apply them? When you compute for the principal stresses, you can already apply them. So S1 mean equals to, or let me write down the equation. Here is, the center is half of your sigma, right? And here is top. So the radius will be square root of sigma squared over 4 plus tau squared. So your principal stress 1 is half of sigma plus sigma squared over 4 plus tau squared. And your principal stress 2 is the one with minus, right? And now we are applying the stress concentration factor. So if we for the mean values, they're 0. So you don't need to do anything for the mean ones because they are 0. So only care about the amplitude. Okay? The amplitude one, that means they are, remember when we are trying to apply stress concentration factor, you have static load, dynamic load, you have a normal stress, and the shear stress, right? So for static, you have KT and KTS, and here you have KF and KFS. So now, since they are the fluctuating part, so we are focusing on these two Ks. So right here, you should be using KF sigma over 2 plus KF sigma squared over 4 plus KFS tau squared. And for similarly for the other one, the same. Sorry. You need to Oh, yes. That's correct. And then right here, Kf sigma over 2 minus Kf sigma over 4 squared plus Kfs tau squared. Okay? And for the figure, I already gave you bending and torque. So when you are trying to get normal and static, you will read this diagram for Kt. And for the torque, torsion, and static, that will give you Kts. Okay, so you have 4 figures. This is 4 figures. The left figure 1 on the left upper corner gives you Kt. The one on the right gives you Kts. And then use the 2 figure at the bottom. That gives you Q and Qs. Okay? Q and Qs. And using the 2 equations I gave you, you can compute for Kf and Kfs. So the entire solution process is like this. Start from the shaft analysis, finding out the worst loading position, and then try to study what's going to happen when the shaft is rotating. And you realize the bending moment and the twisting moment doesn't change with time. The only thing that's changing is the position of the element on the shaft. So bending moment and torque doesn't change with time. The amplitude part of N and T are 0. However, when you are studying for the von Mises stress is about the stress inside the material. And because the material is rotating, so it's experiencing some periodic change of the stress. So that's why you, after observing the situation, you realize the element on the top, when it's on the top, is being pulled left and right. When it goes to the bottom, it's being compressed. So it's pull, compress. The stress is like a sine wave. Okay? Since it's a sine wave, so the mean value is 0. The only thing you need to care about is the amplitude. Next, when you apply for the Soderberg model, which is the one with yield strength and the endurance limit. So this is the one. This is the Soderberg. So when you plug in this equation, actually you don't have mean part because the mean part is 0. So whatever you get for the von Mises stress amplitude part, plug in right here, divided by the endurance limit smaller than n. So at the end, n will be smaller than St over S von Mises. That would be your answer. For this unique condition, the mean part of the von Mises equals to 0. Okay? So that's how the solution can be determined. Any questions? Did you finish? Okay. Someone finished. Good. Did you get it right? No. Who get it right? Okay, we'll see. So, later on when we do the grading, be nice. Be nice on grading. Because let me tell you why we should be nice on treat you nicely. Because whatever we are doing right here is not 100% accurate. Why do I say so? Take one point as an example. When we solve for the moment diagram, we know the worst bending position is located at 304. It's not right at the position with the highest stress concentration. The position with the highest stress concentration should be located at 300. So there is a 4 millimeter difference. So later on, when you apply the stress concentration factor, you are not applying them at the exact position. So the stress estimation will be slightly off. So if you have some kind of precise measurement tool or some kind of numerical analysis machine and try to analyze the stress level at that position precisely, maybe it's not the same as what we have right now. But this is basically how you can at least get some solution. It's a pretty good estimation, and I would say whatever I'm doing here should be quite conservative, because right at the 304 position, the stress concentration level should be slightly lower than 300. But we still use the same level of K. So we are overestimating the stress. That means we are playing conservative. It's okay to play conservative. Okay, so what I'm trying to say is, to solve this problem, I think there is no true answer. If there is no true answer, then we will study how you solve the problem, if it's making sense. So we won't give you a hard time on scoring. But if you give us blank, we cannot help you. Okay? As long as your solution process is making sense, and you should get some points. And if your solution is getting the same amount of values like mine, you can get full grade. Any other questions? Okay. So that's it. That's everything I want to talk about today. Remember next week's proposal. Okay. Please go